What if I told you that every single flash of color you see in a fireworks display is actually a message? A message sent from deep inside an atom. Well, today we're going to decode those messages. We are going to unlock the fundamental rules of matter to really understand the quantum secrets behind all the color and light we see. Let's dive in. You know, this whole story kicks off with a really simple question. We've all seen fireworks light up the night sky, right? With these brilliant reds and greens and blues. But have you ever stopped to think, why those specific colors? Why isn't it just a random splash of light? It turns out this isn't just a pretty show. It's a clue. It's a secret message being sent to us from the atoms themselves. And today, we are going to crack that code. Okay, so the first key to solving our mystery is understanding light. Light travels as an electromagnetic wave, and what defines it, what makes red red and blue blue, is its wavelength. Now, the colors our eyes can actually see are just a tiny, tiny sliver of a much bigger electromagnetic spectrum. And here's the crucial part. Each color corresponds to a very, very specific wavelength. And this is where it gets really interesting. When you heat up an element, it doesn't just glow with some random color. Nope, it emits light only at very specific wavelengths. This collection of wavelengths is called its spectrum, and it acts like a unique, unforgeable atomic fingerprint. Every single element has one. And if we can read that fingerprint, well, we can understand the atom itself. So how does an atom's internal structure even create this unique fingerprint? The first person to really connect these dots was the Danish physicist Niels Bohr. His model of the atom was, well, it was beautifully simple, and it was a revolutionary leap forward. Bohr's model was built on two brilliant ideas. First, he pictured electrons moving in these fixed, stable orbits around the nucleus, kind of like tiny little planets in a solar system. Each orbit has a specific energy level. And second, and this is the game-changing part, an electron can jump from a higher orbit down to a lower one. When it does that, it has to release that extra energy, and it does so by spitting out a particle of light with a very specific wavelength. And boom, that's what creates those sharp lines in the spectrum. Bohr's model was a huge success. I mean, it perfectly predicted the spectrum of hydrogen. But just when it seemed like the mystery was solved, a new problem popped up. When physicists looked closer with more powerful instruments, they saw something they didn't expect. Those single spectral lines, they were actually made up of clusters of even finer lines. And Bohr's simple, clockwork atom had absolutely no explanation for this. The mystery just got deeper. So yeah, these fine lines showed there were some serious cracks in Bohr's beautiful model. It was a fantastic first draft for sure, but it wasn't the whole story. So the search began for a better, more complete answer that could explain what was really going on. The first attempt to sort of patch the model came from Arnold Sommerfeld. He suggested that, hey, in addition to Bohr's perfect circles, maybe electrons could also travel in elliptical paths, ovals. This introduced more possible energy levels for the electron to hang out in, which helped explain some of those finer spectral lines. It was a clever fix, but it was still just a patch. I mean, the Bohr-Sommerfeld model worked okay for hydrogen, but it completely fell apart when you tried to predict the spectra of atoms with more than one electron, like helium or lithium. The model was fundamentally broken. It was becoming clear that a simple fix wasn't going to cut it. Science needed a revolution. And that revolution was the quantum mechanical model of the atom. This new model threw out the entire old idea of neat, predictable paths and replaced it with something much, much stranger and way more powerful: the fuzzy world of probabilities. Okay, this next idea is a huge shift in how we see reality itself. Bohr's orbit was a definite path, like a train on a track. You could say, the electron is right here. But the new quantum model gets rid of that completely and replaces it with this idea of an orbital. An orbital isn't a path. It's more like a cloud of probability. We can no longer say the electron is here. We can only say it's likely to be found somewhere inside this region. It's a huge difference. So an orbital is just that, the region of space around the nucleus where you have the highest probability of finding the electron. It's not a hard shell. Not at all. Think of it more like a statistical map of where the electron tends to hang out. This concept, this is the foundation of our entire modern understanding of what an atom is. Now, if electrons are just living in these fuzzy clouds of probability, how is anything organized? How do you build an atom? Well, it turns out there's a very clear and actually pretty elegant set of rules that govern how electrons build an atom, level by level. So how do we keep track of everything? Well, every single electron has a unique address made of 4 quantum numbers. Think of it like this. The principal number, N, that's like the city. It tells you the main energy level, how far from the nucleus it is. The angular momentum number, L, that's the street, and it describes the shape of its orbital. The magnetic number, ML, is the house number, telling you how that orbital is oriented in space. And finally, the spin number, MS, is kind of like which person is in the house. It can only have one of 2 values, which we call up or down. And here's the key. No 2 electrons in an atom can have the exact same 4-part address. Okay, so armed with those quantum numbers, we can basically build any atom using 3 simple rules. First, there's the off-bow principle. Electrons are kind of lazy. They always fill the lowest energy orbitals first. Second, the Pauli exclusion principle. Any single orbital can hold a maximum of 2 electrons, and if it does, they have to have opposite spins. And third, Hund's rule. When you've got orbitals of equal energy, you put 1 electron in each before you start pairing them up. And that's it. That's the recipe.
All right, we have just taken a super deep dive from fixed orbits to fuzzy orbitals, from clear paths to pure probability. We now have the quantum rulebook for building an atom. And with that, we have everything we need to finally solve our original mystery. So, let's go back to the fireworks.
And here it is. The brilliant color of a firework is quantum mechanics in action, happening right before our eyes. Every element, like strontium for that brilliant red or copper for the blue, has a totally unique electron configuration, based on those rules we just talked about. When you add heat, its electrons absorb that energy and leap up to very specific, higher energy orbitals. But they can't stay there for long. As they inevitably fall back down, they release that extra energy as a particle of light with a precise wavelength, that element's unique fingerprint. That is the brilliant, pure color that we see lighting up the sky. So, we solved the mystery of the fireworks, but we're left with an even bigger, more mind-bending idea. At its most fundamental level, the universe isn't built on certainty, but on probability. The solid table in front of you, the air you're breathing, it's all governed by these fuzzy quantum rules. So it leaves you with a final thought to chew on. If the very building blocks of our reality are based on chance and not certainty, what does that really mean about the solid, predictable world we think we experience every single day?